Hi everyone, let's jump into some inheritance review. So earlier on, we learned we can create subclasses or child classes using the extends keyword. The class definition is the same, except for at the very end, we state that this class we're creating extends another class. A class can only extend one superclass, as opposed to, say, interfaces, where you can implement multiple interfaces, no problem. Subclasses inherit all fields and methods from the superclass. However, we can't directly access private fields or private methods because private fields and private methods can only be accessed in the class they're defined. And since they weren't defined in the child class, we have to use the super keyword to get around this. We can access private fields by using super or calling getter methods defined in the parent class. But if we don't have getter methods, it will be difficult or impossible to access those fields. Additionally, constructors are not inherited. Fun fact in Java, constructors only work if they have the same name as the class. So since constructors defined in the parent class don't have the same name as those in the child class, then we won't be able to use those constructors. But once again, we can use the super keyword to get around this by passing in the type and number of parameters of the constructor we want to call from the superclass. In addition to inheriting state and behavior, subclasses can contain new fields and methods not defined in the superclass. So we can add fields and methods, new methods, no problem. And if we wanted to change the behavior of a method from the superclass, we can override an existing method. This uses the exact same method header, so method name and number and type of parameters, to completely change the behavior of a method. Or we can overload a method, where we use the same method name, but change the type and or number of parameters to create multiple methods with the same name that do different things. Super cool. If we wanted to use the implementation of a method that we say overridden in its child class or subclass, we can once again use the super keyword to use the superclass's implementation of the method. So an example we saw from section was the vehicle class, and then creating subclasses called car and bus. So our vehicle class has two fields, license and on, a constructor, and three methods, start, get, license, and num passengers. And we can create two child classes using the extends keyword. Both of the child classes call the parent constructor using the super keyword. And the car class defines a new method wear seatbelts, as well as the bus class defines a new method make stop. However, if you notice inside of make stop, we have to call the num passengers method of vehicle in order to access the num passengers field, since fields are private and must be accessed via a getter method in child classes. And we can create these inheritance diagrams which illustrate which classes extend from which becomes super handy when we have many classes in our inheritance tree, and especially when we're trying to figure out whether or not a declared type can be of actual type later on. To illustrate some polymorphism, overriding or overloading existing methods from parent classes, we can use vehicle, car, and bus once again. Now you notice inside of car, we overloaded start, where in the parent class, our start method doesn't take any parameters. We introduce a second start method inside of car that takes a single string model parameter, which in addition to turning on or setting on to true, we're also printing driving my and then whatever the given model is. And inside of bus, we see an example of overriding an existing method. So instead of simply turning on to true, our bus's start method without parameters will set on to true, as well as print the wheels on the bus go round and round. Very cool. So one of the key points with inheritance is every subclass has a single implementation of all methods defined either in that subclass or defined in a parent class. So looking at our vehicle and car example, car defines a method wear seatbelts, but it also has a start, get license, then passengers method from vehicle, right? Because these are all the methods that were either defined in car or its parent class. However, given a method call in a subclass, which implementation of that method do we use? So there are two main attributes to keep track of. First, does that method exist? Was it defined in the current class or one of its parent classes? And two, if it does exist, we should use the most recently defined implementation of a method. If a method's defined in a subclass or current class, we should use that. Else, we look into its parent class for that method implementation, and we keep going up the inheritance tree. When we have many subclasses and their inheritance diagrams are very, very full, method calls are difficult to keep track of. So we can use what I like to call inheritance grids. So for an inheritance grid, we have class along the top, vehicle, car, and bus. And for this example, we're going to be using the start methods. So the start method without parameters and the start method with a single parameter. Note, there's no conventional way to do this. I just like having the class on the top and the methods on the side. However, feel free to choose whichever you like more. Vehicle, car, and bus all have a start method implementation without parameters. Vehicle, it has one it defines. Car, we do not touch the start method without parameters. We add or overload start by adding a second start method that takes in one parameter. But for the start method without a parameter, we use vehicle's definition. However, bus does override the start method in vehicle by giving a new implementation to start without parameters. So vehicle and car will both use vehicle start method, while bus will use its own definition. Now, looking for the start method with one parameter, vehicle and bus do not have an implementation for start with a single parameter. However, car, we do add a start method that takes in a single parameter model. And we can denote a method implementation on existing with an X, and that car contains a start model with a single parameter by stating car.start model to show that car does indeed contain a start method with a single parameter. Another way to do this is to directly put whatever is outputted by a method in the grid as opposed to the class and the method calls. I like to do this first one because the second one does work if your output is simple and it's trackable, right? Like it prints something. However, if your method performs multiple actions, the output method of filling out the grid can start to become messy. So I like to do the first one, but if a method prints out a single line, feel free to go for the second one. Moving forward, we have this concept of a declared type and an actual type. So it looks like this, where we have the declared type on the left and an object's actual type on the right. And we've seen this before with, for example, list and an array list, where our declared type is a list and our actual type is an array list. Now, Java programs will treat the Java object as a type declared type, but the object's behavior or its methods will be determined by the actual type. So one example we can give using our vehicle classes is we can define a myCar variable of declared type vehicle and of actual type car, where we can substitute myCar for all places that require a vehicle. However, the methods inside of myCar will be cars methods. And the actual type must be of the same type or a subclass of declared type. This is how I like to think about it, but another way to do so is to say declared type must be the same type or a superclass of actual type, whichever one is more intuitive to you. So you may recognize this example from section, and let's say we're defining a new variable called myGame. Its declared type is game, while its actual type is video game. And I'm going to use a green arrow to represent actual type and red to represent our declared type for the rest of this video. In English, this makes sense. Our video game, all video games are games, so it's okay to declare a video game as type game. However, all video games are not Minecraft, so it's not okay to declare a video game as type Minecraft. In Java, this makes sense as well, because all video games extends or inherit from game. So we're guaranteed to have all states and behavior from game inside of a video game. So it's okay to declare a video game as type game since it contains a version of the fields and methods inside of game. However, if we try to do Minecraft, my game is equal to new video game, there's no guarantee that video game contains all the states and behaviors as Minecraft. Maybe we added a field or a method that's not contained in video game in its child class. So this is where we'd get an error. But for this example, it's okay, like we said. Video game is a subclass of game. And then for our Fortnite example, or similar to my Minecraft example, and also we have a game called My Car. Maybe forgot to change that from the slides. If we look at this, our actual type is of type video game. However, our declared type is Fortnite. And since there's no guarantee that video game contains all the states and behaviors from Fortnite, this is not okay. We'll get a compiler error. So with declared and actual types, if a declared type is incorrect, i.e. actual type is not the same or a subclass of declared type, we'll get a compiler error. Additionally, if we're trying to execute a method that is not defined in the declared type, we'll also get a compiler error. So in this example, if we defined a car with declared type vehicle and tried to call start of model 1, even though car contains an implementation for start with a single parameter, since vehicle does not, we'll get a compiler error. Since Java will treat our actual type car variable as a vehicle, and vehicle does not have an implementation for start with a single parameter. Furthermore, we have this notion of casting. And casting is treating an object of one type as if it were an object of another type. And as we've seen in some of our inheritance mystery examples, we can cast using casted type in parentheses, and then casting our variable of another type, and then attempting to call a method on that casted variable. Another way I like to think about this is we're temporarily assigning an object to have a declared type of casted type. So it's like we're temporarily giving an object a different declared type. And the same rules apply. So casted type must be the same or a superclass of actual type, and actual type must be the same or a subclass of casted type. And why casting is useful? Well, let's say we're calling a method on an object that is not defined in its declared type. However, we know that this method that we're trying to call is defined in either a subclass of declared type or an actual class, or maybe both. So in this case, we can temporarily cast this object to have a different declared type so we can successfully call a method that we know is defined without raising a compiler error. So using our vehicle example once again, let's say we have two objects. A vehicle, Brett's bus, with type actual bus, and another vehicle called Casey's V, which is of actual type vehicle. If we tried to cast Brett's bus to a bus, right, will this work? Well, it's the same rules as declared and actual type. So since our actual type is bus, we can cast or temporarily give this bus object a declared type of either bus or vehicle, looking at the inheritance tree. And we're casting this to bus, so that cast is okay. Next, we have to look at our start method that we're trying to call. As we know from our inheritance grid example, bus does have an implementation of start, so this is perfectly okay. And we can use our arrows once again to help visualize this. The casted arrow or casted type is above our green actual type, so this is okay. Another visual representation I think is handy. A second casting practice problem. So now with Casey's V. So we attempt to cast Casey's V with actual type vehicle to a car. But this isn't okay, right? Our declared type or casted type must be a parent class or the same class as our actual type. Looking at our inheritance diagram, if our actual type is vehicle, we cannot cast to anything below vehicle in our inheritance diagram, which in this case we're trying to do with car, so we'll get an error here. With casting types, or errors involving casting, there are two possible errors we can raise. A compiler error, when we're trying to execute a method that is not defined in the declared type or not defined in the casted type. Even if actual type contains implementation of that method, like we saw earlier with the compiler errors, if the declared or casted type does not contain that method, we will throw a compiler error. Additionally, we may encounter a runtime error, like this would be the error that would be thrown in Casey's V example. And this is when the actual type is not able to be casted to the casted type. And this is opposite to the compiler errors, where if the actual type cannot be declared as the declared type, we would throw a compiler error. For casting, we will throw a runtime exception, because casting does not occur until after program compilation. So we won't know, or the Java, whatever program you're trying to run, won't know that you incorrectly casted until it reaches that line of code. So that's why it's a runtime exception as opposed to a compiler error. So we can put all of this information together into this flow chart where it tells us the steps of making a method call, right? If we're casting or not, what error we'd throw at each step if we ran into an error, else which we would execute the method. I kind of have my own version of looking at this. So this is what I call the inheritance method call lookup algorithm. So the first step depends on whether you're casting or not. If you're not casting, then we'll check and throw a compiler error if actual type is not the same or a subclass of declared type, or if declared type does not have the method we're trying to call. Great, just a simple error check. If we are casting, then we'll throw a runtime error if actual type is not the same or a subclass of declared type, or if declared type does not have the method we're trying to call. And if we get past all of our error checks, the second part of this algorithm is to perform actual types method. So we can either look up the method bound to actual type in a table if we made one, or in the inheritance grid, or we can look for the most recent method definition in our inheritance tree. So start at the current actual type class, and then work our way up until we find the most recent method implementation. Great. Let's get some practice with our inheritance mystery from Ed. So here's the inheritance diagram from Inheritance Mystery 1, where we have a fire class, an air class, and earth class that extend fire, and a water class that extends earth. And let's fill in our inheritance grid, starting with fire and working our way towards water. So we look at fire, and we have a method definition for method 1 and method 2. So fire contains method 1, and fire contains a fire.method 2. And let's make a note that fire.method 2 calls the method 1 inside of fire. So this will be helpful when we're chaining multiple method calls together. And just for a note for this problem, each method call prints out the class and method we're calling. So fire1 will print out fire1, and this will just help speed the process along as we're trying to figure out what will be outputted where. For earth, we override method 1 from fire, so we will print earth1, and then call the super or fires method 1, and method 2 is not touched. So earth will contain a fire.method2, which will also call our method 1. However, fires, so we will call fire.method2, which we'll call method 1. However, method 1 is bound to earth's method 1 since we overwrite it. So earth method 1, as we touched on earlier, will print out earth 1 and then call fires or its superclass's method 1. And that's how we end up with this table. Moving on to air. Air extends fire, so it inherits method 1 and method 2. It doesn't override or overload method 1 or method 2. However, it does add a new method 3. Awesome. Finally, for water, water overrides method 1 and method 3, and it inherits earth. So there's no method 2 implementation in earth. So we work our way up the inheritance tree, and water will inherit fire's method 2, which will print fire 2, and then call whatever method 1 is bound to. And in this case, our method 1 inside of water simply prints water 1. And bam, we complete our inheritance grid. Finally, let's use this grid to complete some practice problems and walk through the inheritance method lookup algorithm. Great. So let's say we have a variable of declared type fire and of actual type earth. We wanted to call var2.method1. Will this work? There's no casting, so we need to see if it compiles first. So the declared type is fire and the actual type is earth. Earth is a subclass of fire, so we're good. Next, we need to see if the declared type contains method 1. Fire does contain a method 1, so that check passes as well. Finally, we need to look up which method we're going to call. So the actual type is earth, and we're calling method 1, so we'll be calling earth method 1. So earth method 1 prints out earth 1, but we also call fire method 1, and we'll print out fire 1 as well in our lookup table. Isn't that cool? We have an algorithm now. Another example, we have a variable 4 of declared type fire and of actual type water. And we attempt to call, that's a typo, it should be var4.method2. Pretend that's a 4, please. The declared type is fire, and the actual type is water. Water is a subclass or a sub-subclass of fire, so this is perfectly okay, as long as the green arrow is at the same level or below the red arrow. Now, does fire contain a method 2? Yes, it does. So now we hop over to our actual types implementations of method 2. So water is our actual type. We're calling, okay, that arrow should be pointing to method 2. Sorry for the confusion. We will call this method. So water implements fire, or the method 2 inside of water is fires.method 2. So this will print fire 2, and then call water.method 1 and print water 1. Another example with a variable 2 with declared type fire and actual type earth. Earth is a subtype of fire, so this is perfectly okay. Fire contains a method 2, so we're good. And now we hop over to our actual type of earth and our method, method 2. Once again, the arrow, don't worry about it, it's fine. But we will call fire method 2, which subsequently calls our earth.method 1. So we'll print fire 2, hop up to earth, print out earth 1, and then earth 1 calls fire 1 and print out fire 1. Whoa, jumping all over the place. But with this inheritance grid, it's easy to keep track of. Finally, let's do a casting example. So we have a variable 6 called var6 of declared type fire and of actual type air. Now let's say we tried to cast it. This is var6, not var2. But anywho, to be casted type of water. So temporarily declaring the type as water. Will this work? Well, first, earth is a subclass of fire, so this method declaration is okay, no compiler error will be thrown. However, the casting type is water, And water is not a parent class or the same class as Earth. In this case, the casting type or temporarily declared type is below the actual type in our inheritance diagram, and this is not okay. And since we're casting, this will throw a runtime exception, and our program will throw an error. Super cool. That's my entire inheritance review. I hope that this may have given you some tools to help you further on with these types of problems. And yeah, good luck on quiz 0.